Right now, thousands of tons of aluminum are hurtling through the sky surrounding major airports, separated by mere miles in zero-visibility clouds. To manage this density, air traffic controllers rely on a pristine interface. They look at flat panel displays, packed with flight numbers, real-time altitudes, and exact ground speeds, plotting perfectly choreographed approach paths. These alphanumeric tags are actually generated by a separate digital process, overlaid on top of the physical radio returns, to make the scope readable for the controller. If you strip away the digital maps, the leader lines, and the identification tags, you are left with a blank screen, displaying nothing but fading green blips. Those raw blips are the output of primary surveillance radar. It is a system built entirely on passive physics. Specifically, it works by bouncing powerful radio waves directly off the thick metallic skin of an aircraft and simply waiting for the return echo. A raw radar return provides exactly zero information about what that object is. It doesn't tell the altitude, the destination, or its identity. To safely sequence dozens of heavy jets through blind conditions, aviation engineers had to construct an active data loop to bypass the limitations of those passive electromagnetic echoes. The entire tracking architecture originates on the ground, at the primary radar dish. This equipment generates and focuses massive bursts of ultra-high and super-high frequency electromagnetic energy, sweeping them outward in a tight beam. These radio pulses obey the strict laws of electromagnetic propagation. They travel at the speed of light, precisely 162,000 nautical miles per second. Because that velocity is a physical constant, tracking an aircraft becomes an exercise in Teilneichment. The ground station simply calculates the microsecond interval between firing a pulse and detecting the faint reflection bouncing off a metallic hull. To find the target's distance, you take the speed of the wave, multiply it by the measured time interval, and divide by 2. The time must be halved because the measured interval accounts for a round trip. The aircraft's exact compass bearing is calculated by recording the physical angle of the rotating radar dish at the millisecond the echo is caught. Historically, controllers viewed this exact geometry on a plan position indicator, where a spinning electron beam synchronized with the dish outside to paint targets onto a cathode ray tube. Primary surveillance radar effectively translates microtime into macro distance, but it only works if that return echo makes it back to the receiver uncorrupted. Ultra-high frequency waves travel in rigid straight lines, creating a geometric challenge for long-range tracking. Because the Earth is a sphere, the curvature of the planet creates a hard physical boundary where the radar's line of sight simply terminates. We plot this limit using a formula. Maximum range equals 1.22 multiplied by the square root of the altitude. At 10,000 feet, the detection limit is 122 miles. Below that boundary, aircraft drop into a radar shadow and vanish. Even when aircraft remain well within the line of sight, passive radar struggles with signal clutter. The reflection off a small aircraft is physically weak. It is easily drowned out by the massive surfaces of mountains, urban buildings, or the heavy precipitation inside a thunderstorm. Relying entirely on passive echoes leaves airspace vulnerable to blind spots and weather degradation. Safe sequencing requires an engineered failsafe. The solution sits directly on top of the primary radar dish, in the form of a smaller, rectangular antenna array. This is the Air Traffic Control Radar Beacon System, more commonly known as secondary surveillance radar. Instead of waiting for a passive physical echo, this secondary system initiates an active interrogation and response loop. As the secondary antenna sweeps the sky, it transmits a highly specific coded interrogation signal designed to trigger a specific piece of hardware. To complete the loop, the aircraft must carry the corresponding avionics, a transponder. When the transponder detects the ground station's interrogation, it does not act as a mirror. It actively fires back its own high-energy, precisely timed radio pulse. Because this reply is a fresh, high-power transmission generated by the aircraft itself, it easily punches through dense weather cells and ground clutter. This active broadcast removes the reliance on surface area and material reflectivity, turning the airframe into a source of information rather than just a reflector. Because the transponder manufactures its own reply pulse, engineers realized they could embed digital data directly into that transmission. This diagram displays the first layer of encoding, Mode A. It embeds a 4-digit numeric squawk code, giving the controller 4,096 options to identify targets. On top of that identity layer, the transponder stacks a second data packet called Mode C. Mode C interfaces with a blind encoder inside the aircraft to report pressure altitude. It uses a fixed datum of 29.92 inches of mercury, ensuring the controller receives a standardized altitude reading regardless of the cockpit altimeter. The modern iteration, Mode S, pushes this further by hard-coding a permanent, unique hardware address into the airframe. With a unique address locked in, controllers can use a feature called select addressing. They can data link text clearances and weather reports straight to the cockpit, bypassing congested voice radio frequencies entirely. Identity, precision altitude, and text data links. By stacking these modes into the radio pulse, controllers secure the exact digital profile required to manage dense airspace. All of this encoded data gets put to work when controllers execute terminal area vectoring, mapping out precise arrival paths for incoming traffic. Relying on the transponder's position data, the controller issues specific heading instructions, sequencing multiple aircraft smoothly onto a shared final approach course. When a pilot accepts radar vectors, they stop flying published routing. They hand their navigational trajectory over to the controller, trusting the ground station's spatial geometry. That trust is underwritten by the Mode C altitude readout. The controller constantly monitors that data packet to ensure the aircraft never descends below minimum vectoring altitudes, keeping them safely above terrain. Managing high-volume traffic with primary radar alone forces controllers to increase separation distances significantly. Without automated identification and altitude reporting, individual targets are more difficult to track, reducing the maximum capacity of the terminal airspace. Armed with active transponder data, controllers can safely compress the spacing between arriving jets, maximizing the number of aircraft that can use a single runway. By replacing passive physical echoes with active data loops, aviation engineers established the high-density environment required for modern global transport.